Peter Frazier for agreeing to talk to us about Bayesian optimization. Peter doesn't need introduction, but I'm going to do an introduction nonetheless. So this is the official bio. So Peter Frazier is an associate professor in the School of Operations Research and Information Engineering at Cornell University, and he's also a staff data scientist at Uber. He received his PhD in operations research and financial engineering from Princeton University in 2009. His research is in optimal learning, including Bayesian optimization and incentive design for social learning with applications in e-commerce, the sharing economy, and materials design. He is an associate editor for operations research, so send your papers there. ACM Tomax, another option, and the IISc transaction, so that's 3 options. And he is also the recipient of an AFOSR Young Investigator Award and an NSF Career Award. With that, I'll hand it over to Peter.
Thank you. Great, so it's a real pleasure to be able to be here and to talk to you about Bayesian optimization. And I hope that I'll be able to talk about some methods that you might find useful in applications that you work on. And I also hope that some of you find these methods interesting enough to go and do methodological research and to create the next new awesome Bayesian optimization algorithm. So is it too loud? Or is it, it's good? OK. Great. So Bayesian optimization is focused traditionally on solving this mathematical optimization problem. So I have an objective function, capital F, that takes vector valued input in d dimensions. And historically in Bayesian optimization, the dimension of the input space has been small, where here I'll mean less than 20 dimensions. Through all of the tutorial, I'm going to focus on the setting where the feasible set is a simple set. You can think about just a box, a hyperrectangle. There is work relaxing that and thinking about constraints that are more interesting. But for this tutorial, let's focus on simple constraints. The objective function f is continuous, but it lacks other special structure. In particular, it's not concave, it's not convex, it's not linear. And that's going to mean that many methods that are really good when those assumptions are met, those methods are not going to be able to solve this problem where my objective is no longer concave. When I typically, in Bayesian optimization, when I evaluate the objective, I get only the objective value, and I don't get any gradient information. And so this is going to make it also challenging to use a traditional optimization method that's based around the ability to observe gradients. And evaluations of f are what we call expensive. So usually what this means is that each evaluation takes a long time. Maybe it takes 10 minutes, maybe it takes an hour, maybe it takes a day. It could also mean that the evaluation actually does cost money. This may happen if you're running your experiments on Amazon Web Services and you need to pay $100 each time you run an evaluation because you're taking up a lot of compute time. Or in some of the applications that I work on, it could mean that each evaluation, in the context of material science or drug discovery, I may need to buy materials in order to do the experiment, and that's also expensive. And the expense of each evaluation, what that's going to mean is that the number of times that I can perform the evaluation is limited. So in a problem with a problem in, let's say, 5 dimensions, a typical number of evaluations I might be allowed to do would maybe be 200. Okay? And moreover, evaluations of f might be noisy. Through the first part of the tutorial, we'll focus on the noise-free setting, and then I'll talk about noise. And when noise is present, the typical assumption that's made is that the noise is independent and normally distributed with common but unknown variance. And then there's some work that can relax that assumption. So this problem shows up in lots and lots and lots of applications. The application where this particular class of methods called Bayesian optimization methods is most widely used is for tuning hyperparameters in machine learning models, especially deep neural networks. Tuning a deep neural network, can take, several hours on a system with a bunch of GPUs, and I ideally would like to explore the space of different hyperparameter settings for my neural network. I might want to choose, the number of neurons, the number of layers, the dropout rate, the learning rate that I use when I run stochastic gradient descent, a variety of these parameters. So I'd like to try out a bunch of different configurations for my neural network, train each one, evaluate it, and find the one for which validation error is the best. So this fits the assumptions that I just showed you because each evaluation is expensive. I typically don't get gradients when I do my evaluation. There's no special structure, that says that when you change the number of neurons, that validation error would be convex that would allow me to use a convex optimization method. So this is, in practice, currently the most important single application of Bayesian optimization. So this problem that I described also shows up when tuning algorithms via backtesting. So for example, you can imagine at Uber, the dispatch system, the system that determines which car to send to come pick you up when you request a ride on the Uber platform, that dispatch system has a bunch of parameters in it. We have a simulator, and you could imagine using that simulator with a particular set of algorithm parameters in order to evaluate the quality of those algorithm parameters with respect to some metrics that have to do with efficiency, quality of the rider experience. And that simulator, it's a simulator, so it's not going to give you gradient information. It's not going to have any special structure. It's going to be expensive to evaluate. It'll take many hours to do a run. So finding the set of algorithm parameters that maximizes quality according to these metrics would fit into this optimization of expensive functions framework that I described. A place where I got started in doing Bayesian optimization was in collaboration with Yelp. I had a PhD student who had written part of his dissertation on Bayesian optimization, and he went to work there. And when he got there, he realized that they have a lot of tunable parameters that show up in the algorithms that they use to run their business. For example, the algorithm that ranks search results has a bunch of tunable parameters in it. So you type in, coffee near San Francisco, California. It chooses to provide this rank ordered list of different, coffee places, some of which you might be interested in. So the problem of choosing those parameters to maximize some metric is an optimization of expensive functions problem, where the way that we evaluate the quality of a particular set of algorithm parameters is we run an experiment, an A/B test on live user traffic, where we split each request on the Yelp website into two groups, one of which gets a control set of parameters, and the other one gets the set of parameters that we're interested in evaluating. And we then take the difference in whatever metric we care about, maybe ad revenue, engagement, and then attempt to maximize that difference. Okay, and then I talked about using optimization of expensive functions in the context of tuning a dispatch algorithm where you're using a simulator in order to evaluate quality. You can also do more or less the same thing, where the way that you evaluate quality of a particular set of algorithm parameters for a dispatch simulator or a pricing algorithm is by running a real-world experiment. Maybe an A/B test, maybe what we call a switchback experiment, where we alternate back and forth between a treatment set of algorithm parameters and a control set of algorithm parameters. Just two other applications that are also important. So one is in tuning engineering systems, choosing parameters in engineering systems. My group does a fair amount of work in helping aerospace engineers design aircraft, where the way you evaluate quality is by running computational fluid dynamics simulation, modeling airflow over a wing. Again, these are expensive to evaluate. You don't get gradients. And in materials design and drug discovery, where here the thing you're interested in doing is designing a molecule. So you have a parameterized class of molecules or a parameterized class of peptides. And the way you evaluate quality is through a lab experiment, which might take a day, might take a week. So Bayesian optimization is a class of mathematical methods for solving these problems. I'm going to come down. The way that these methods work is they start by building a statistical model. Typically, actually always when it's called Bayesian optimization, a Bayesian statistical model on the objective function f. And in practice, this statistical model is almost always a Gaussian process prior. And if you haven't seen those, I'll explain how those work in a moment. So I have this statistical model. The statistical model may come from an initial set of evaluations of the objective that I've done in some simple way, maybe uniformly at random, or maybe those evaluations of the objective function were chosen by engineers who were trying to solve this problem without using a formal optimization method, or maybe that prior distribution is based just on conversations with domain experts who know about this problem. And so we start with this Bayesian prior distribution on the objective function f, and then while our computational budget is not yet exhausted, we're going to use this statistical model in order to define an acquisition function, where the acquisition function measures the value of an evaluation of the objective at a particular point x. We then find the x that maximizes that value of the evaluation. We sample the objective at that point, and then we observe the objective value. Then we take that evaluation, we update our statistical model, and we repeat. Okay? So here's what that looks like in an example where I'm maximizing a one-dimensional function where my evaluations occur without noise. So the top here shows the input x on the x-axis, all right, and values of the objective on the y-axis. I've done 3 evaluations, which are shown here with blue circles, and I fit my statistical model, my Gaussian process regression model. The way that Gaussian process regression works is that at a particular point where I haven't done an evaluation, I don't know the objective. And in Bayesian statistics, whenever we don't know something, we model it as being drawn from a probability distribution. So the probability distribution that Gaussian process regression uses is the normal distribution. So for example, at this point, 150, the statistical model says that the value of the objective is normally distributed with a mean equal to the height of this solid red line and a confidence region given by the lower and upper limits of this dashed red line. So Gaussian process regression says that the objective is distributed normally with a mean and standard deviation given by the solid red line and by the dashed red lines. Then based on this statistical model, at each point along the x-axis, I compute this acquisition function. Okay, and I'll talk a lot about how we compute that. But first, what I just want to note is that it's doing something reasonable. All right, so at points where I've already evaluated, like here at 100, I have this evaluation. At that point, the acquisition function is equal to 0. Okay, also here, and also over here. At points where I have a lot of uncertainty about the objective value, for example, this region here and this region over here, the acquisition function is high. And that's because when I really don't know very much about the objective, it's valuable to learn. Also, at points where the estimated value of the objective is high, so sort of in this region here, high relative to everywhere else, the acquisition function also tends to be high. And that's because my goal is to solve an optimization problem, and evaluating points where the objective is predicted to be good is informative for solving this optimization problem. So then what the Bayesian optimization algorithm would do is use a traditional optimization method that uses gradients, maybe Hessians, in order to find a global optimum of the acquisition function, okay, which would be this point here. Then it would choose to do an evaluation at that point. So we get this new evaluation. We update the posterior, okay, recompute the acquisition function, re-optimize it, get this point, evaluate there, and repeat. Okay? And after hopefully a small number of samples, if we've done a good job with our statistical modeling, we found an approximate global optimum efficiently. One comment that I'll make is that we have to optimize this acquisition function. It may seem a little silly. We started out with one optimization problem, and then we said in order to solve that, we're going to actually solve a whole sequence of optimization problems. So how have I made the problem easier? Well, the acquisition function, unlike our original objective, is cheap to evaluate. We're talking 15 milliseconds. And you can get gradient information, and you can get second order information. All right, cool. So that's an introduction to Bayesian optimization. What I want to do is, talk about Gaussian process regression, describe how that works. Then I want to describe the acquisition function that I just showed you in that animation, which is by far the most widely used acquisition function and is good enough to get you, with kind of good practical results in a wide range of problems. Then I want to talk about some more specialized things, which I think are practically useful, but also are closer to the frontier of research and should help illustrate some of the ideas that you may want to pursue if you're interested in doing research in this area. So one is doing parallel Bayesian optimization using this expected improvement acquisition function. And the second one is doing, again, parallel Bayesian optimization where I get gradient observations of my objective and or my evaluations are with noise. And here I'm going to present a different acquisition function, which is called the knowledge gradient acquisition function, which works a lot better for these kinds of problems and also for a variety of other sort of more exotic problems. Then I'll show you code. There's good codes implementing all of this stuff, so I'll give you some pointers and then have just a brief discussion of research directions. Any questions before we dive into it? Yeah. Yeah, so the question is, do we always assume that we get a global solution? The goal in Bayesian optimization is to get an approximate global optimum. We're not satisfied in this setting with the local global optimum. I won't talk in detail about the theoretical guarantees associated with Bayesian optimization. They tend to be much weaker than the kind of theoretical guarantees that you would get, for example, in convex optimization. So you typically don't actually get a perfect global optimum, but as you expend effort, these methods will approach a global optimum. Other questions? Yeah. So typically okay, so the question was, do I allow infinite support for my objective function? So typically people are assuming compact support. Any theory that you look at, you're going to assume compact support. In practice, if you use an optimization method for maximizing the acquisition function that is for solving unconstrained problems, and if you make sure that the statistical model that you use does something reasonable, sort of decays nicely as you go out to infinity, then you can get away with doing unconstrained Bayesian global optimization. Yeah, but in practice, most people are assuming like some compact support. Okay, cool. So Gaussian process regression. I showed you an animation of kind of the flavor of what that looks like. Again, so I'm going to be predicting mean values for my objective and then confidence regions for what the objective might be. So in order to, how many people already know Gaussian process regression? And how many people like have done Bayesian linear regression? Okay, cool. So if you've done linear regression, Bayesian linear regression is like linear regression, except I assume that the value that I'm trying to estimate through linear regression was drawn from a probability distribution. And what this assumption does is allow me to do reasonably good inference when I have a small amount of data. Gaussian process regression is very much like Bayesian linear regression, except that I'm estimating an infinite number of parameters, and I'm able to do this in order to do function approximation. So what I want to do to illustrate Gaussian process regression in a way that hopefully will be understandable for people that haven't seen any of that is just to start simply with picking 2 points in my feasible domain, x and x prime. And I'm interested in inferring the value of a function. So let's just start by trying to infer the value of the function at these 2 points. All right? So x and x prime, these are going to be fixed. And then any given function will induce values for the pair f of x and f of x prime. All right? And then let's put those guys in a vector. Okay? This vector. So this function, the value of this function f at x and x prime can be represented by this particular vector for which f of x is on the horizontal axis and f of x prime is on the vertical axis. If I have different functions, then I get different vectors. All right? So I'm going to be interested in inferring the value of I'm going to be interested in inferring the value of the function at one point, f of x prime, given information about the value of the function at the first point, f of x. And what I'm going to do is I'm going to do Bayesian linear regression. The first step in doing that is to put a probability distribution on the data I'm going to get, f of x, and the thing that I want to infer, f of x prime. The probability distribution that I'm going to use, because it's Bayesian linear regression and things are going to work out nicely, is a normal distribution. So I'll put a multivariate normal prior, and a multivariate normal prior has a mean vector. In order to create the mean vector, I'm going to assume that I have a function, mu0, which I'm going to evaluate at the 2 points x and x prime, okay, and create a vector. in practice, what people usually do is they take mu0 to just be a constant. Okay? And actually, often the constant is 0. So you can imagine there are just zeros plugged in here. And then I have another function called sigma 0. People call this the kernel, or the covariance function. It takes 2 arguments, and typically it's a function that's going to decrease when the difference between its 2 arguments it's actually going to increase. So it decreases as this thing gets bigger. And you'll see in a moment why that's true. But what I'm going to do is I'm just going to evaluate that function sigma 0 at every pair of points, x and x prime and x and x prime, and x prime, x prime. Okay? And there's going to need to be certain regularity conditions which are imposed on sigma 0 in order to make this a covariance matrix. In particular, it's going to need to be a semi-definite function. So what I'm picturing here is a contour plot of the density of that probability distribution on the pair f of x and f of x prime over here. So in the absence of data, this contour plot is telling me how likely it is that that the vector fx prime fx, takes any given value. What you see is that the probability density is sort of squished. It's squished in this direction, right? It's narrower in this direction than it is in this direction. And so what that's really saying is that values along the diagonal, holding everything else equal, are more likely than values kind of way down here and way up here. In the context of this picture, what that's saying, so what does it mean for this vector to lie along the diagonal? Well, that's going to happen when f of x and f of x prime are equal to each other. And the vector's value is going to fall close to the diagonal when f of x and f of x prime are close to each other. So what we're doing is we're saying that, it's more likely than not that the value of the function at x and x prime are similar to each other. And the way that we choose our, typically for most choices of the covariance kernel, sigma 0, when x and x prime are close to each other in the input space, this density is going to be more squished. So we're going to say as x and x prime get closer together, we think it's more likely that f of x and f of x prime are close. All right, so let's say that I observe the value of the function at one point, f of x. So what that's telling me is that the vector has to be along this line. All right? Its f of x prime component has to be equal to the height of this blue square. So then what I do in Bayesian statistics is I start with my probability distribution over the thing that I don't know, this vector, and given data, I compute the conditional distribution. The meaning of this data is that I need to be along this line. Okay? So then the conditional distribution is the height of this contour plot, the height of this density, but just along this line. Okay? So if you think in three-dimensional space, if you think of this popping out, this is like a hill, where the summit is here. And then I have a slice coming down like this into the blue line. And the posterior distribution of f of x is the profile of that slice sticking out into the third dimension. And I can compute the center of that profile. And I can also calculate, the standard deviation, sort of how wide it is. And that's going to turn out to be a normal density, just a univariate normal density. and I can calculate its mean, and I can calculate a confidence region. And so what I'm doing is I'm plotting that right here. Okay? I can do the same calculation, but instead of using x along the horizontal axis, I can use the density that I would get by plugging in a different x prime into that original multivariate normal density, right? And I would get, I said that when the 2 points are closer together, the densities tend to be more squished. So you would get, you'd get a more squished density. And then when you think about what the profile, the slice into the third dimension looks like when I cut through it along this blue line, it's going to be more narrow. Okay? So what Gaussian process regression does is to take that same calculation and to generalize it into multiple dimensions. The way that I do that is I think about any collection of k points in the input space of the function that I'm trying to do inference over. And I'm going to define a probability distribution over how likely it is for this k-dimensional vector to take any particular value. And I use the same procedure. I take mu0, which is this mean function. I evaluate it at each of the input points. Again, this is typically 0. And then I evaluate my kernel or my covariance function at each pair of points in order to get a covariance matrix. Then I do Bayesian linear regression using observations at a collection of points with the one point that I haven't done an observation at as the thing that I'm calculating the conditional distribution over given my data. And it turns out that the math that you get out of that is really simple and nice and easy to calculate. So in particular, the posterior on f of x prime, given the value of the objective function at any collection of n points, is normally distributed with a mean and variance given by these expressions. Okay, and if you're used to doing Bayesian linear regression, these will look sort of alarmingly familiar. Great. And actually, this formula assumes that this thing is 0. You get something slightly more complicated if you don't assume that. And a nice reference for all of this is Rasmussen and Williams 2006, which is linked in which is in the tutorial, the written tutorial, which is on the archive, and I'll have the link at the end. All right, cool. Any questions about that? Great. So in theory, that's all you need to do. In practice, from an applied point of view, it's really important to specify the covariance kernel, and it's more important to specify the covariance kernel, and the mean function usually works out okay. So how do we choose the kernel and the mean function? So what's typically done is you designate a family of functions that you think is going to work reasonably well for modeling your data, and then you take an initial stage of samples, often uniformly at random, and then you choose the member of that family using one of 3 methods. The one that's easiest to code but the least robust is you use maximum likelihood estimation, where you calculate how likely is my data under this multivariate normal distribution as a function of the parameters of the parametric class of the class of covariance functions that I used. Okay, and then you optimize over those parameters in order to find the one that makes your data most likely, and then you just fix those parameters in stone. Second one is maximum a posteriori estimation, where you say, well, I don't know what, so the parametric class of covariance kernels and mean functions that we use, we often call the parameter that specifies the member in that class a hyperparameter. So we just, we talk to domain experts. We think about, what's reasonable in our problem. And we put a prior distribution on these hyperparameters. And then instead of doing maximum likelihood estimation, we do maximum a posteriori estimation, which basically is going to regularize your solution towards more reasonable values for these hyperparameters. And then the third thing that if you need this to work well in an application that people do is to use fully Bayesian inference where we sample from the posterior distribution on the hyperparameters and then take a mixture of Gaussian processes. And if you're not a Bayesian and that didn't make sense, don't worry about it. So then, OK, that's kind of a general approach. What do people actually do in practice? So the parametric families that people use for the mean function are either a constant or this is like probably 95% of what you see. And then if you're working in some special application, like an aerospace application, and you work with a bunch of aerospace engineers, and they're like, I really know that the drag is a function of this particular parameterization of the wing that you're optimizing over. I know it like roughly kind of looks like this, and maybe it looks like this. In that setting, you would use a prior that looked like this, and you'd sit with them and you specify some basis functions, and then the beta 0 and then the beta j's would be the parameters of your family of mean functions. And then you'd either use a non-informative prior or a uniform prior or a normally distributed prior. And you're probably only doing this if you're like working with aerospace engineers, domain experts, and using something like this. And the most common thing is this with this. And then the covariance kernel, the important thing is that as the distance between x and x prime gets bigger, the covariance should get smaller, so that when points are further away, we think it's less and less likely that the value of the function at those 2 points is close to each other. So this is the squared exponential. Often people take p is equal to 2, and it's the Gaussian kernel, or a power exponential kernel, people call this. And then this is the Matern kernel. And it's a little bit more complicated, but in many applications, actually, this is kind of both simple and works pretty well most of the time. And just to give you some intuition, by changing the parameters in the kernel, you determine different amounts of wiggliness in your function, right? So by setting one set of parameter values, you can say that, I think my function is really smooth, or I think it's really wiggly. And with multidimensional problems, you can control the wiggliness in each dimension through the hyperparameters. And that's probably the most important. When you think about putting a prior on the hyperparameters for your kernel, if you know something about how quickly something varies in each dimension, that's the most important information to encode in your prior. Great. And then just like from a practical point of view, I recommend doing cross-validation, where what you would do is you take evaluations of your expensive to evaluate objective function. You then iterate it through them. You hold one out, pretend you haven't observed it, run your statistical model in order to make a prediction for what the value of the objective at that point will be, and then compare that prediction to what it actually is. And one way to do that is to make a plot that looks like this, where each time you hold out one data point, you put a point here. And on the x-axis, you put the actual value of the point. And on the y-axis, you have the predicted value for the point based on Gaussian process regression. And if predicted and actual are very close to each other, these points should line up along this diagonal line. And of course, they're not going to perfectly line up because you're making predictions with uncertainty. But what you should look for is that so here this is the predicted value, and this is say a 95% confidence region for the value of the point based on all of the data except that. What you should see is that if this is a 95% confidence region, then about 95% of the points should have the confidence region intersecting the line, this diagonal line. it's a simple diagnostic to make, and you can find out sort of early on in a way that's easy to diagnose that your statistical model is giving you garbage, and you can fix it before it causes a real problem. Cool. All right. And then you can incorporate noise relatively easily through the whole, you just go through the Bayesian linear regression, but with noise. It's easiest in the case where noise is homoscedastic, the variance of this is the variance of the noise. In practice, we don't know what that is, and we include it as a hyperparameter and estimate it as part of our model. If you're using Bayesian optimization, say for optimizing a queuing system, and the variance of the queuing system blows up in certain regimes, it might be important to allow the noise to depend on where you sample. That's a little bit more sophisticated, but there are methods for doing that, and kind of the way that they work is you put a Gaussian process prior on the variance, and then you do sort of conditional Gaussian process-based inference given the variance. Cool. Any questions? Yeah.
Yeah. So you said that the way that you choose the prior is by talking to an expert.
Yeah.
So, but often you have data, you look at the data. And
Yeah.
So can you talk about the effects of doing this and how it affects the rest of the?
Right. Okay. So the question is, get the prior. I talked about getting the prior by talking to experts, but what does that actually look like in practice? And yeah. So there are really two kinds of applications of Bayesian optimization. One is a heavyweight application where the function evaluations are super expensive, where super expensive, let's say, means a day or more, and you're willing to put the work in to fly out to the client site and have day-long meetings with them and explain what Bayesian optimization is. So in that setting, yes, you are talking to domain experts, and the benefit of doing that is that, let's say you go from 300 evaluations in order to find a pretty good optimum. You go from that to maybe 200 or 150 on a 4-dimensional problem. There are other kinds of applications where function evaluations are, let's say, take a minute, and so getting from 300 down to 150 function evaluations is going to be saving you 150 minutes. You're not willing to jump on a plane, to San Francisco in order to do that savings. So in those situations, you're not really doing anything sophisticated in terms of talking to domain experts. You're just doing kind of 50 evaluations chosen uniformly at random, and then you're using a matern kernel with a non-informative prior over the hyperparameters, and you're giving up the ability to have domain expertise make you more efficient, but it's okay. So those are kind of like the two domains. Yeah. I also kind of have this theory that people use Bayesian optimization so much for tuning deep neural networks that there's like a conventional wisdom about what kinds of kernels you use and what kinds of priors over kernels you use. And I think that kind of conventional wisdom has built up in a way so that it tends to work well for the problems that people usually solve with these methods. Other questions before I talk about expected improvement? Cool. All right. So expected improvement is the most widely used acquisition function. If you just remember, we did a whole bunch of statistical inference about our objective, and then now we want to use that statistical model in order to decide where to sample. Expected improvement is derived using a decision theoretic argument. So here I'm going to be minimizing. Imagine that this is my posterior after n evaluations. If I were to stop now and report as my final solution to the optimization problem the best value that I had evaluated, I would suffer some loss. Okay? And that loss would just be, that minimum value, which I'll call f star. On the other hand, if I do one more evaluation, that's going to change my posterior, and it's going to reveal the value of the objective at the new point that I choose to evaluate, f of x. And if I were to stop and report a solution after that new evaluation, its value would just be the minimum of the old optimal solution and the new point that I had evaluated. The benefit, the reduction in loss that I get due to that single sample is just the old value, f of f star, minus this new value, the minimum of f star and f of x, which I can rewrite in this way. So it's f star minus f of x, the positive part of that quantity. Now, before I evaluate at x, I don't know what f of x is. But I have this Bayesian posterior distribution over the objective, so that gives me a probability distribution for f of x. So the expected improvement acquisition function, what it does is it takes the conditional expectation of this improvement under the time n posterior distribution. That's what this n means. And that's defined to be the expected improvement. So just a statement is that by construction, evaluating at the point with the largest expected improvement is the optimal thing to do in the following specific setting. So in the noise-free setting, if this is the last evaluation that I can make, if I'm risk neutral, so I'm interested in maximizing expectations, and I'm only willing to report as a final solution a value that I have previously evaluated. Okay, now I'll return back to this point later. So something that's not important in theory, but it's super important in practice and is a big part of the reason that expected improvement is so widely used, is that you can rewrite it in terms of the normal CDF and the normal PDF, and compute it really easily. So it has this super nice expression, which depends on, so delta n is just the difference in value between the function value, the previous best function value after n evaluations, and the posterior mean at the particular point x. And it also depends on the sigma n is the standard deviation of the posterior at the point x, and this is the normal PDF and the normal CDF. So here's what it looks like if you plot a contour plot with respect to this delta n, where larger values of delta n correspond to points whose posterior mean is better. And then larger values of sigma n correspond to points about which we're more uncertain. So you see that expected improvement is largest when the posterior mean is good and the posterior standard deviation is high. And in Bayesian optimization and also in multi-arm bandits, people talk about the exploration versus exploitation trade-off. That means that on the one hand, I want to evaluate things that I don't know about. That's exploration. But I also want to evaluate things that I believe are good. That's exploitation. So in this setting, evaluating sort of at kind of over here with high sigma n is exploration, and evaluating over here at x's with high delta n is exploitation. And so expected improvement is defining one particular way to make this trade-off between these two quantities. All right. So then again, I'll just show you this animation, which brings things together. And this is the Gaussian process prior, and then this is the expected improvement acquisition function. And so we just evaluate at the point that maximizes the EI, update the posterior, and repeat. OK? Great. And so, all right. Any questions about the basic expected improvement acquisition function? Great. Cool. So if you have a problem, that's in 10 dimensions and you get noise-free evaluations, and you don't get derivatives, and you can only do one evaluation at a time, then the method I just described actually works really well. And you can take links to the code that I'll give at the end and just use it, and hopefully you'll be a happy camper. Now, let me talk about two other settings, sort of representative of the larger class of of problems that go beyond the standard problem. And let me first talk about what you can do with parallel observations. All right. So the expected improvement acquisition function actually parallelizes in a conceptually straightforward way. All right? So I'm going to have Q. I'm going to think about being able to evaluate the expensive to evaluate objective function at Q points in parallel. So x1 through xq are those Q points. Maybe each of those points could be in 1 dimension, or they could be in 5 dimensions. Okay? So if you remember expected improvement, right? So the improvement when I was just doing a single evaluation was the old best minus the value that I saw. If that value was negative, then there's no improvement. But if that value is positive, then there's an improvement. So the way that I'm going to generalize to parallel evaluations is that now the best point that I'm going to have observed among the Q that I'm about to evaluate is just the minimum of the function values at each of those points. So I can define a generalized expected improvement. People call it the multi-points expected improvement, or the QEI, where Q is this Q, which is just defined like this. Here's a picture of what that looks like. This is a problem with a one-dimensional input. The posterior mean is given by the dashed green line. I've evaluated without noise at each of these x's. And the blue line is the actual function, okay, unobserved by the algorithm. So the QEI is a function of, in this case, 2 scalar inputs. The first point I'm going to evaluate and the second point that I'm going to evaluate, and I'm going to do those in parallel. What I'm plotting here is this QEI function, a contour plot of that QEI function. And also the gradient of that QEI function with these little arrows. So one thing that you'll observe is that there tend to be local minima of this function along the line x1 is equal to x2. x1 will be the first point I evaluate, x2 will be the second. That's because this is a problem without noise. So if I'm already evaluating at a point, I don't want to evaluate there again. All right? Also, so there you notice the aspect ratio is not 1-to-1, but this function is symmetric. And that's because this function is symmetric, because x1 and x2 are interchangeable with each other. There's a global maximum of this function here and also symmetrically here. What does this correspond to? Well, that's the point x1 is equal to, let's say, 1.6, and x2 is equal to 0.6. So that corresponds to putting one evaluation here at 1.6 and the other evaluation here at 0.6. So finding the point, the vector, that maximizes the QEI does something really reasonable. First, it balances exploration and exploitation like QEI from the point of view of evaluating points with, so 1.6 has a low posterior mean and a high variance. 0.6 also has a reasonably low posterior mean and a reasonably high variance. But we get diversity, right? So I'm doing these evaluations in parallel. If I were only to, if I were to calculate the regular EI once, that might be maximized here. And then if I maximized it again, I would have another point that would be close by. So somehow the decision theoretic analysis that underlies this is smart enough to know that I don't want to have my evaluations be too close together, right? I want to, given that I'm already evaluating here, it's a lot less valuable to evaluate close to that, because after this evaluation is done, I'll have a reduction in variance. So my second evaluation is much better to have over there. All right? Now, one of the challenges with parallel EI is that it's harder to optimize than the one-dimensional EI, because there isn't a nice closed form expression, at least not in terms of things that are easy to compute. There's a closed form expression in terms of kind of arbitrarily high dimensional multivariate normal CDF, but that's not easy to evaluate. So here's a mathematical method that actually works really well and allows us to optimize the Q-dimensional EI and actually generalizes much more broadly to being able to develop Bayesian optimization acquisition functions for problems where it's hard to compute them in closed form. There are two steps. The first is to come up with an estimator, a gradient, an estimator of the gradient of the QEI. And then the second step is to use that gradient estimator within multistart stochastic gradient ascent. Okay? So here's how that gradient estimator works. I'm going to write down, I'm going to let y be the value. I switched from uppercase f to lowercase f. Y is equal to the vector, which is the value of the objective at each of the Q points that I'm considering evaluating. Under the Gaussian process posterior, that's multivariate normal. Therefore, it has a mean vector and a covariance matrix. I'm going to let M be that mean vector, and I'm going to let C be the Cholesky decomposition of that covariance matrix. And so what that means is that if I were to draw a vector of independent standard normals Z, y would be equal in distribution to this expression, just the mean plus that Cholesky decomposition times this standard normal random variable. And the expected improvement can be written as the expectation of this particular function of y. With that knowledge, what I can do is rely on something that's called infinitesimal perturbation analysis. And how that works is basically, if certain regularity conditions are satisfied, you can switch derivative and expectation. Right? So I'm interested in the derivative of EI, which is the expectation of this thing. I'll just rewrite that as the expectation of the gradient of h of y, where I remember that y is written like this. Z, and this is the gradient with respect to where I measure, x1 through xq. Z doesn't depend on that. It's just a standard normal random vector. But M and C do. All right? So that makes it really easy for me to construct this gradient estimator. I just simulate a vector of independent standard normals, calculate the mean vector, calculate the Cholesky of the covariance, and then my estimator of the gradient of the QEI is just obtained by differentiating this non-smooth function with respect to the x and the implicit dependence of M and C on x through the chain rule. Okay? Then once I have that stochastic gradient estimator, I use multistart stochastic gradient ascent. If you're not familiar with this method, it's an awesome method. You should check it out. You select a variety of starting points uniformly at random, and then starting from each starting point, you do stochastic gradient ascent, where you run that simulation that I just described in order to get a random variable whose expectation is equal to the gradient of the QEI. You take a step in the direction of that gradient, where the size of the step is modulated by a decreasing step size, alpha n, and then you repeat. And then what will happen is that as the number of iterations of that algorithm goes to infinity, each of those, the path that you get from each starting point, for example, this is showing the sequence of, so this is x1 and x2, this is the QEI surface. I chose one initial starting point at random, then I'm calculating the gradient of, I'm simulating the gradient of the EI, I take a step in that direction, I take another, I do that again, I do that again. I'm multiplying the size of these steps by smaller and smaller numbers, so I'm slowing down which is controlling my noise. And then what will happen is that eventually I'll converge to a stationary point of the QEI surface. Then for each of those points, I use simulation in order to determine which one of them has the largest QEI. And then that's the set of points that I run, at which I run my expensive simulation. Here's an animation showing the QEI surface, the objective function that I'm minimizing here. So I've evaluated it at these red x's. The true function is this blue line. The posterior mean is this dashed green line. Here I'm showing the paths of stochastic gradient ascent. So I'm doing multiple starts, so I have multiple paths illustrated by the different colors. This is the iteration number of stochastic gradient ascent. So what you see is that it'll bounce around or it'll increase, and then at some point it will converge. And I'm showing you the operation of QEI, of parallel expected improvement, in an asynchronous setting, where I'm showing in a star, with a star, a point that I'm currently evaluating my expensive computer simulation on. So what I would like to do is I'm going to maximize over the QEI surface, saying that one of the evaluations that I choose has to be equal to this one that I'm already got going, because I don't want to kill it and restart it. Okay, so in this two-dimensional image, that corresponds to being stuck on this blue line, right? Pegged at 0 because this thing is evaluating at 0. So what I do is I run multistart stochastic gradient ascent, but where I optimize not over the whole thing, but over only along this line. And what ends up happening is that it finds the global optimum here. And what I'm doing in this image is I'm plotting the slice through, I'm taking this slice through this three-dimensional surface. All right? And you see that there are two local optima of the QEI, one here on the left-hand side of where I'm measuring, and one here on the right-hand side of where I'm measuring. And this one is bigger because the posterior mean is lower here, and I'm measuring there. Okay? Don't worry about the green line. Just focus on the orange line. The orange line is showing the global maximum of the QEI. So I choose to sample at that point. I start a simulation there. I start an expensive evaluation there. Then the core that's running this evaluation finishes, or the node that's running that evaluation finishes. I got one running here at 0.5. So I rerun the whole thing, where now I'm stuck on where I have the new QEI surface. I'm stuck on this line. This is what the slice of the QEI surface looks like. I find the global maximum, which is here. I start an evaluation there, and then when that guy finishes, I repeat. Okay? This thing scales pretty well. I'm showing the difference in quality between the global optimum and the point that we think is the global optimum for a six-dimensional problem, standard test problem called Hartman. And I'm running the algorithm that I just described, and I'm running another approximate algorithm that was developed when we didn't know about this stochastic gradient ascent infinitesimal perturbation analysis thing called CL mix. And so just what I want to call out is that if you focus on the solid lines, those are all computed using the algorithm I described, using a code base called MO, Metrics Optimization Engine, that you can use if you want to use these in applications or just try them out. And so you see go from like this is progress versus iteration for 2 cores, 4 cores, 8 cores, 16 simultaneous evaluations, 32, 64, all the way up to 128. And you see significant speed up even for large numbers of cores. So this is a way that you can leverage parallelism that you have available to you in order to find approximate global optimum more quickly. Cool. All right, any questions? Yeah. Yes. That's right. So that's why we do, yes. So when you do stochastic gradient ascent, the place where you converge to on the QEI surface, which determines where you're going to evaluate, depends on where you started. So I think this is the global optimum. If you start from a bad starting point, you'll converge to a suboptimal local optimum. So that's why we need to do multiple starts. And then our in our codes, we worry a lot about how many starts to do, and that should be based in principle on how many local modes we think there is in the QEI surface, and we think that that depends on how many points you've previously evaluated. So there's a whole technology there. And it's even led me to do research on efficient multistart stochastic gradient ascent. Yeah, so it's a good point. Other questions? Yeah. Yeah, so you can plug, yeah, probably I should be doing that. I made this slide a couple years ago. You could plug in your favorite stochastic gradient ascent algorithm. And that's probably going to work better than, I think I did this just because I didn't want to explain momentum, because yeah. Cool. Other questions? Yeah.
In practice, when you apply multistart, you always get to the global optimum?
You don't always get to the global optimum. If you choose it, what's that?
Or very close.
You need to have one start that's in the basin of attraction of the global optimum. So there's always a chance that you fail to do that. We try to balance, if you're like super nervous about that, you can have a large number of starts. That's what we do, yeah. I think there's a research question that's actually not called out at the end of the deck, but is like more efficient computational implementations of kind of existing Bayesian optimization technology. And there's probably something that you can do that's more intelligent than choosing starting points uniformly at random. There's probably like whole sections of the space where the global optimum doesn't live, and so we can avoid those. It may even be possible to slice it up so that we know that it's unimodal in each region. The thing that ends up being true in practice is that the price of failure is not that high. If your SGE doesn't work at all, what ends up happening is that you end up choosing points uniformly at random, which is not great, but choosing points to evaluate uniformly at random is a competitive enough method for global optimization of expensive functions that you usually will see that as a baseline in global optimization talks. So if a couple of your evaluations are like closer to that than something sophisticated, it's not like your method is going to fail.
But for sure it is better than the single start.
Oh yeah, for sure it's better than a single start, yeah. Cool. Other questions? Okay, great. Cool. So before just sort of wrapping up, the last section that I want to tell you about is knowledge gradient methods and how they're used to do parallel Bayesian optimization when you have noise or gradients. And these methods expected improvement is great for sort of the class of problems that I've described to you, but then when you get outside of it, it tends to not work very well. And so you need a more sophisticated acquisition function, and the knowledge gradient acquisition function is one that sort of is more robust across a broader range of problems. So I want to think about global optimization, not local optimization, with a non-convex objective where evaluations are expensive, and I get gradients. All right? And I'm going to present this work in the context of complete unbiased, possibly noisy gradient observations, but this similar techniques, sort of a generalization of this technique is also able to handle incomplete gradient observations and then biased gradient observations in the parallel setting. So it turns out that Gaussian process regression generalizes really nicely to gradient observations. The way to kind of get an intuitive understanding of that is a gradient observation is kind of like observing the difference in value between 2 points. You know, like a finite difference approximation is observing that, and a gradient is like close to a finite difference approximation. And when you observe linear functions of vectors on which you're doing Bayesian linear regression, inference is actually really nice, really clean, because normal random variables and linear functions play really well together. So what goes on in Gaussian process regression when I have gradient observations is I think about a function that maps the input x onto not just f of x, but onto the vector f of x and the gradient of f. All right, so I have a Gaussian process prior and that multi-output Gaussian process prior. And then I run through that same inference procedure that I described before, but for that vector-valued mapping. What you get when you do that is a new kind of posterior distribution, which is also a Gaussian process. I'm showing here, so this is an evaluation of an objective at 1, 2, 3, 4 points without gradient observations. Here I'm doing Gaussian process inference, including gradient observations, these red lines, the slopes of these red lines. And you'll see that the posterior is narrower, especially at points that are sort of close to where I'm evaluating. All right? So inference works great when we go to gradient observations, but the acquisition function is going to turn out there's a problem. So here, just remember the motivation for the derivation of expected improvement. I had the loss if I stop now is the minimum point I've evaluated, f star. If I take an additional sample after evaluating at x, the loss that I'm going to suffer is this minimum. And then the reduction in loss due to sampling is just the difference in those quantities. That's if I don't observe gradients. So if I do observe gradients, it turns out that when you're observing without noise, when I add in this gradient observation at f, it actually doesn't change at all this value. I already knew f of x. Okay? I'm learning more about the function. I'm just not learning more about it at the point that I've evaluated. And so what ends up happening is that the expected improvement actually is unchanged from the case where I'm not observing gradients. Effectively, what this is causing to happen is that expected improvement is putting no value on gradient information, and that runs contrary to our intuition as optimizers that gradient information is like the most valuable kind of information you could get. And as a consequence, expected improvement can make bad decisions. So here's a posterior distribution. Here's the expected improvement. It's maximal here. So it says I want to evaluate at this point. That's a point where, if I evaluate there, I am going to get an improvement. I'm not going to learn a whole lot about the objective, but if this really is the last evaluation that I can make, yeah, it's probably a good choice. But if I can do 2 more evaluations, it's a really bad choice. It would be much better to do 1 gradient evaluation here. It's probably the case that the value I'm going to get is not going to beat this point. But then I'm going to learn basically everything I need to know about the function kind of in this regime. If the gradient points that way, if the gradient's pointing down in that way, then my next evaluation can be over here. And that's pretty likely to find a new global minimum. If, on the other hand, my gradient evaluation is like sloped up like this, then my next evaluation will probably be over here. Okay, so gradient, it seems like if I'm getting gradients, I should probably evaluate over here, not there. So if you remember, the derivation of expected improvement is optimal under these assumptions, right? This is our last evaluation. We're risk neutral. We're in the noise-free setting. And I'm only willing to select a previously evaluated point as a final solution. So what I'm going to do is I'm just going to drop that last assumption. Okay? And it's going to turn out that the point to evaluate that's optimal under this reduced set of assumptions is something that we can compute and something that works really well. And it's what we call the knowledge gradient acquisition function. Okay? So now the loss, if we stop now, since I'm not restricted to returning as my solution a previously evaluated point, is this minimum of the posterior mean. I'm calling that mu star of n. If I do one more evaluation of f and its gradient, then the loss that I'll get under this reduced set of assumptions is the minimum of the new posterior mean mu star n plus 1. Okay? And in particular, you'll notice that this evaluation was not lower than f star. So under the expected improvement acquisition function, if I observe at this point and I get this value, there's no improvement. F star is equal to the minimum of f star and f of x. But actually, there's a great improvement, right? Because you know, in my next evaluation, I'll probably be able to evaluate here and confirm that this point is really good. And you know, and under a risk-neutral decision maker, you know, knowing that this point has this low expected value is really valuable. So what we do in this knowledge gradient acquisition function is we just take the difference between mu star of n and mu star of n plus 1. That's the reduction in loss due to sampling. That's a random variable at time n. But we can take its expected value, and that's the knowledge gradient acquisition function. How are we doing on time? 10 minutes? OK, great. And so as a consequence, this new acquisition function is going to explore a lot more effectively than expected improvement when we're getting gradient observations. So I'm starting these. So on the left, I'll have, so dkg is like kg with derivatives. I have the posterior that I'm starting with that I'll use the kg acquisition function for. Here I'll have the same posterior I'm starting with that I'll use for the expected improvement acquisition function. Expected improvement wants to sample here, okay? And the kg acquisition function wants to sample over here. All right? I'll do an evaluation. Expected improvement will find a better point, but kg will have learned a lot more about the objective in this region. Okay, and in particular, it will have learned that kind of this is a promising region to explore, and its next point is going to be to evaluate there. Okay? Right? And so at this point, kg has found a substantially lower minimum of a posterior mean in this region that's unexplored for expected improvement. Okay? And so that advantage, expected improvement, will start to catch up, but then we'll fall behind again. And so actually, let me not do that just yet. And so what ends up happening is that when you run numerical experiments, especially on higher dimensional problems where gradient information is even more valuable and even more important to take advantage of, you get substantial improvements in performance. So this is running parallel Bayesian optimization, where this is on a log scale, the regret, the difference in solution quality between the previously evaluated point that we think is best and the actual global optimum, comparing against a variety of different methods, including DEI. So this is derivative-enabled knowledge gradient. This is the expected improvement. We're also running just multistart LBFGS, so not a Bayesian optimization method. And you'll see sort of consistently, not in every case, but that you get a lot of value by doing this. I'll just say a little bit about computation, where the way in which we compute and optimize the knowledge gradient acquisition function builds quite substantially on the way that I described how we optimize the parallel EI. So here's how we can compute it. In a loop, we simulate, so we're proposing to evaluate the objective at these q points, x1 through xq. We simulate the value of the objective from the posterior along with its gradient at those points using our Gaussian process posterior. We then minimize, so for that simulated value of the observation, we can compute what the new posterior mean would be, and we can minimize that using a continuous optimization solver like BFGS. And then we can compute the reduction in loss, right? And then if we average that many times, that gives us the knowledge gradient. So the way that we can optimize that is, again, using this infinitesimal perturbation analysis and an additional idea from the envelope theorem. So we're interested in the gradient of the knowledge gradient. That's the gradient of this expectation, where I'm including the dependence of the minimum of the new posterior mean on the value I observed and where I sampled. So I'll switch derivative and expectation under some regularity conditions to get this expression. So now what I need to do is to calculate the derivative of this quantity with respect to x. This doesn't depend on x, so I can get rid of it. And so now I just need to calculate the derivative of this. This is the derivative of the minimum over a dummy variable x prime of the new posterior mean. Okay? And I can write the dependence of y in the same way that I wrote it with parallel EI in terms of a random variable z whose distribution doesn't depend on x. Right? So I have deterministic functions that depend on x, and then some exogenous independent random variable. So the envelope theorem says that if I'm taking the gradient of the value of the solution of a parameterized class of optimization problems, in principle, I need to worry about the fact that the location of this minimizer depends on the thing I'm taking the gradient with respect to, because it does. Right? So I need to think about that complicated interaction. But the envelope theorem says that under some regularity conditions, I can ignore that. Right? So I can just solve this optimization problem for the given z and x, call that x star, and then I can just calculate the gradient of this posterior mean, holding this x star fixed. So this mu n plus 1 has an analytic expression from Gaussian process regression, and then these also have analytic expressions from Gaussian process regression, and I just calculate that using the chain rule. So the resulting procedure is just I simulate standard normal random vector, calculate the mean and the Cholesky decomposition of the covariance matrix of my new sort of larger observation, because I'm getting gradients. I find the minimum of what the posterior mean would be under that simulated output. And then I get a stochastic gradient estimator obtained by using the chain rule and differentiating the posterior mean, holding this x star fixed. Okay? So this procedure works really well when you have gradients. It also turns out that it improves substantially over expected improvement if you don't have gradients, but you do have noise. And that's because the whole derivation of expected improvement relied on noise-free evaluation. And as soon as you have noise, that breaks. Okay? But this modified approach is more robust to that. So here we have QKG in purple. And then, so for example, this is the parallel EI. Actually, this is also in high-dimensional problems. It tends to provide a lot of value. So this is noise-free on a three-dimensional problem. And then in noise, so in noisy problems in the batch setting, it tends to also outperform. OK, so just to finish up, there's a bunch of codes for doing this stuff that I recommend using. My group has a code, the Cornell metrics optimization engine, which is based on a code that a former PhD student who went to Yelp developed based on the work in his dissertation. We're in the process of, we're accepting bug reports and usability requests. We're just about to release an upgrade to Python 3 for this, and we'll have a conda package, so it'll be easy to install. There's also, this gpyopt is a nice, it's got a lot of features in it. So especially with regard to Gaussian process modeling, if you need to do something funky or fancy, this is a nice package. And then Spearmint tends to be, if it works for you, then you're in good hands. Some of the time, it will crash. There was Ryan Adams, his group developed this code, and then Then they had a startup based on the code, and then Twitter bought the startup, and then they stopped maintaining the code because they were making money off of the sort of improvements to the code. So it's still useful though. There's also, so Scott Clark has this company called, he's my former PhD student, has this company called SIGOPT. They have free use for academic use cases, and they have a really nice API. So sigopt.com is worth checking out. All right, and then quickly kind of research directions. I think applications are fun and awesome, and there's a lot of headroom. These are all one-step algorithms. They seem to work really well in practice. Nobody really understands why, so that's a super interesting theoretical question. Going beyond Gaussian processes, I think, is important. High-dimensional Bayesian optimization. There's a bunch of work in this area I didn't talk about. And then problems with exotic structure like multi-fidelity optimization, optimization with trace observations. All right, cool. Thanks. Yeah, in the back.
What do you find is the most interesting direction for high-dimensional Bayesian optimization?
Yeah, they're kind of, okay, so what's the most interesting direction for high-dimensional? I think there are two fruitful directions that should both be pursued. One is developing statistical models that are good in high dimensions. Like high-dimensional problems that we actually want to solve, I think, are special. So like, how are they special? Understand that, build stat models that are good. Everybody agrees that's true. I personally am not sure that our existing acquisition functions are good in high dimensions. So there might be some like decision theoretic kind of theory that could be done there. Oh, and then the third direction that I think everybody agrees with is better computational methods for actually optimizing acquisition functions over high-dimensional domains.
Okay, so let's thank Peter again.
Thanks.